Lisa Torlina. She's a PhD student in the group of Orgasm Nova in Max Born Institute in Berlin.
So I'd like to start off by saying a really huge thank you to the organizers for having me here today. It's really great to be here and tell you all about our work. So essentially, my talk today is going to be focused on one question. And the question is going to be, how long does the process of ionization take? And there's been a number of techniques developed in recent years to address this question, and I'm going to focus on just one of these, which is known as the Atto clock. And this is actually a really, really nice and elegant approach to the problem. But as we're going to see, to interpret the results, to extract the physically relevant information, we need to have a really good grasp on the underlying theory. And so this is what essentially the focus of the talk is going to be on. Make a change. Okay, that's better. Okay, so first, why do we want to ask this question at all? Well, of course, on the one hand, this is just a very fundamental question. So ionization is one of the most basic processes we have in nature, and asking how long this process takes is, again, one of the most fundamental things we can ask. So it'd be really nice to have an answer. And at the same time, we know that ionization can induce multi-electron dynamics. And so if we can then time resolve ionization, this could enable us to probe these dynamics, which of course would be very interesting from the perspective of attosecond science. So as I said, I'm going to be focusing on ionization in the multi-photon regime. So we're going to be talking about strong low-frequency fields. So something of the order of 10 to the 14 watts per square centimeter, and this talk's going to be about 800 nanometers. So it turns out that in this regime, there's actually a third reason to be interested in the question, how long does ionization take? And this stems from the tunneling picture of ionization. And so I guess most of you are probably familiar with this, but just in case, we have the electric field, the laser, combines with the core potential, and together they form a barrier. And so then ionization can proceed by the electron tunneling through this barrier. And in a linear field, this barrier will oscillate from one side to the other, and in a circular field, the barrier will rotate around. And so it's actually this latter case that we're going to be interested for the purposes of this talk. So if we think about what we have here for a second, we see that we have here the possibility to study tunneling in a time-dependent setting because we have a barrier that moves. And when we ask the question, how long does ionization take, what we're actually asking is how long does an electron take to tunnel through a barrier? And of course, this is something which has been a very long-standing and controversial question. Namely, are there time delays, like real time delays associated with the motion of an electron under a barrier, or does tunneling happen instantaneously? Okay, so how are we going to answer this question? Well, like I said, there's been some really nice experiments which were pioneered by the group of Ursula Keller at ETH Zurich, which has come to be known as the Atto clock. So in this experiment, we take a short, circularly or nearly circularly polarized infrared pulse, and we use this to induce ionization and deflect electrons in different directions. And then we measure the electrons. So we build up a full angle and energy resolved photoelectron spectrum. And the basic idea then of this experiment is that time is going to be mapped to angle, which is exactly what we have in a regular analog clock. So if you look at this clock, we have 120 degrees. We know that that means it's 4 o'clock with the hour hand. So it's exactly the same idea. Except now, the hand of our clock is this rotating electric field vector of the laser, which we know will rotate at a constant rate. And in addition to this, we make sure that we have a short pulse. And because we should have a short pulse, we know that at some point in time, the electric field vector is going to have its maximum length. And so this is going to give us a preferred instant of ionization, and this is going to allow us to resolve a particular time. And so we have a little movie here to show this, to give you just some feel for it. So we have the electric field vector rotates, and as it rotates, it changes its length. So now if we imagine that we're rotating with it, we're rotating with the rotating tunneling barrier, the width of the barrier is going to change as well as it goes around. And so here is the same thing in a static picture. So electric field rotates, the barrier rotates as well, and it changes its width. And so up here, we have the thinnest tunneling barrier, where the electric field is at its maximum magnitude, and we would expect here this to be the highest probability of ionization. And so we would expect that the peak of the photoelectron distribution would correspond to this particular ionization event. Okay, but we need to answer one more question. So after the electron comes out, where do we actually detect it? And we can do this in the simplest possible picture. So the simplest picture looks like this. So if the electric field points up, the electron will tunnel downwards. And then when it comes out, in the tunneling limit, it comes out with a velocity of 0, which tells us that it must move off perpendicular to where it came out. And so we would expect it to detect it here at an angle of 0. And this gives rise to a really, really simple mapping, just a direct mapping between angle and time, which is just what we have in our clock. So angle is just directly proportional to the time of ionization. And so if the peak of our pulse is at time 0 and it points in the y direction, we would expect our photoelectron distribution to be centered at an angle of 0 along the x-axis. Okay, so what do we actually see? Well, what we actually see is something a bit different. So instead of being centered at 0, the distribution is shifted up by some angle theta, which we're going to call the offset angle. And the question is, why do we have this angle? Why is it not at 0? And I'm going to put forward a few proposals. So first, some sort of real tunneling delay. So the electron is spending some real time under the barrier, and as a result, time elapses, and it comes out later than we would expect. The second possibility is Coulomb effects. So there's some sort of interaction between the electron and the core as it moves away, and this is also giving rise to some sort of deflection. And finally, there could be some sort of multi-electron effect. So the electron that's going out is interacting with the electrons that are still in the ion, and this is also leading to some sort of delays. But I want to keep things as simple as possible for us all, so I'm going to exclude the last option by focusing on the hydrogen atom for almost the whole talk. And this is really important because this is going to allow us to calibrate our outer clock. So then we can start looking at multi-electron things later on. Okay, so first, how could a tunneling delay give rise to this offset angle? Well, we go back to our picture. So we have, if we see an angle of 0, we have the time of 0, we have this right angle mapping relationship. So now if we have a positive angle and we apply this same right angle mapping, then this seems to tell us that the electron would have come out at some positive time, sometime after the peak of the pulse. However, we know that here is where we have the thinnest tunneling barrier, and the discrepancy between the two suggests that maybe the electron actually spent some time under the barrier and only came out later than the peak of the pulse. Okay, but now there's another explanation possible. So if we go back to our picture, and now we remember that also there's an extra force on the electron, which is we've got our positively charged core, and it's going to pull the electron back up. And so if we look at the trajectory, it's going to feel a shift. It's going to feel a force up this way, which can also give rise to some sort of positive offset angle. So now I've shown you two completely different ways to get essentially the same physical observable, which tells us we have to be really, really careful with the way we model this process and the way we analyze our results. Okay, so what do we want to do here? Well, what we want to do is find out why we have this offset. So we want to be able to distinguish between tunneling and Coulomb effects. We want to be able to see, is it one, is it the other, is it some combination of both? So that's our first goal. The second goal is we actually want to be able to use this as a clock. So given some angle, we want to be able to map this to time. We want to be able to, read our clock. And we're going to approach this in two ways. So first, we're going to do some numerical calculations. So we're going to exactly solve the time-dependent Schrödinger equation ab initio for the hydrogen atom. And we've done this using 3 independent algorithms just to check that we're getting the right answer. And then we're going to look at an analytical theory, which we call the analytical R matrix, that we've been developing over the last few years at MBI, which is going to help us with the second part of the question, to actually get a mapping between angle and time. Okay, but let's start with the numerics. So, like I said, we did this for the hydrogen atom. And if we look at the photoelectron spectra as a function of intensity, we get something that looks a bit like this. And we can pull out these angles at the peak of the distribution and plot them as a function of intensity, and we get this curve. And of course, we see that at all intensities, we have some offset angle which is non-zero, and we'd like to know why. So now there's something really nice we can do, which is, of course, a lot harder to do with experiment, and we can repeat this calculation for a short-range potential. And we've used this Yukawa potential of this form. So what's nice here, so this is the Coulomb potential. The Yukawa potential looks a bit like this. So in this case, the tunneling barrier is still very much present. I'm sure it has a slightly different shape, but it's very much still there. Fundamentally, the process is the same. But now we essentially have no electron-core interaction after ionization is complete. So if we imagine our electron going through here and coming out of the barrier, here we still definitely have some electron-core interaction. Whereas we look at Yukawa, there's really not much there at all. It's just not going to feel much after it comes out. So this is really nice because it lets us eliminate one of these two effects and discriminate between them to see which one is the one that's causing the offset angles. So now I'll show you the results. So this is the same calculation. So this is now the photoelectron spectra, but for the Yukawa potential. And here we see that it's now centered at 0. So if we add it onto this curve, the offset angles vanish across all intensities. And again, like I said, the only difference between these calculations, the essential difference, is the absence of this Coulomb interaction. So this is a very strong indication that it is Coulomb effects that are responsible for these offset angles that we observe, rather than anything that's fundamentally to do with the tunneling process. Okay, so I think this is quite a good result. So we've addressed the first of our two goals, but as we see from this plot, we're still talking about angles. We haven't actually said anything about times. And this is the same with experiments, this is the same with TDSE. To actually be able to recover times from what we measure, we need some sort of theory that incorporates times into it. And now this is where our analytical theory will come in. So just to give you a really quick rundown on the basic idea of this theory. So the idea is we're going to split space into two regions. We're going to have an inner region and an outer region, separated by a spherical boundary. And in the inner region, we're going to have just bound solutions. So we're going to treat the core potential exactly, or however we can solve it, and we're going to neglect the laser field here, or treat it quasi-statically. In the outer region, we're going to do the opposite. So in the outer region, we're going to have free solutions, and we're going to account for the laser field exactly. And then we're going to add a correction for the core. And we have these Icpeac states that you can read about here that allow us to do this. And at the boundary then, we're going to match these two solutions. And the reason we can do this is we can take the tail of the bound wave function here and match it to the Icpeac part, this Coulomb correction part in the outer region. And this is what's going to let the whole thing go through. And like I said, the nice thing about this analytical theory is that it naturally contains a time. And this is ultimately going to allow us to come up with an angle-time mapping. Okay, but before we get to that, I'd just like to check, I think it's good to check that our theory works. So we've made some approximations here, and it's good to know that approximations are justified. So here I show a comparison of ARM calculations, the photoelectron spectra obtained using ARM, with the TDSE calculations, where ARM is shown in red and the TDSE black dashed. And we see that for quite a decent range of intensities, we get very good agreement, up to roughly 2% or so. So I think we can trust our theory. So now we can proceed to look at the times. Okay, so in ARM, the physical quantity of interest is going to be the ionization amplitude. This is what we calculate. And so, I don't know, we have this first part that comes from the inner region, which tells us about the bound state. And then we have two terms from the outer region. So first, this term, for those of you familiar with this is just the Volkov phase, so the exact solution for electron in an oscillating laser field. And now we have this new term that comes from the ARM theory, which is this correction due to the core within the Icpeac approximation. And the important part here is we integrated over this T prime, and this T prime has a natural interpretation as the time of ionization, if you like. And we have these three phases, and they're all quite large. So we can evaluate this integral using the saddle point method. And we know that the integral will be accumulated primarily at the point where these phases vanish, which is the saddle point TS. And if we solve for it, it's complex. But if we take the real part of the saddle point solution, then we can interpret this particular quantity, as the time at which the electron appears in the continuum, which is exactly the quantity that we're after. This is what we want to know. Okay, so if we go ahead and solve, for this saddle point, we get an expression of this form. So this is this real part of the saddle point. This is our angle of detection. We have a correction coming from the pulse, from the shape of the pulse, and we have another correction coming from this Coulomb term. And now, if we think about this, this is now exactly what we want. So now, this equation here gives us a mapping between quantities that we can measure. So this is the angle of detection, and this is the momentum of the electron. So this is all measurable stuff, and these we can calculate. We have expressions for them. And then on this side is the time of ionization. So we can directly relate the observables to this time that we want to measure. And actually, if we look at this part, this is just the simple mapping we had before. It just turns out now this simple mapping wasn't quite right. We were missing a few things. It's not quite as simple as just in a clock where we can, when it's a simple linear relationship between angle and time, we also have to account for these two extra terms. And so now we know how to get a time from our photoelectron spectrum. We find the peak, and then we just have to evaluate each of these quantities at the peak to find the most probable time of ionization. Okay, and just to give you a feel for how this is going to work on our pictures from before, so if we have this positive offset angle, the first part, like I said, is this right angle relationship, this really simple mapping. But then we need to subtract off the envelope correction and the Coulomb correction, which both happen to be negative. And this tells us that the time of ionization is actually somewhere back around the peak of the field. Of course, I've just drawn this picture, so you better not trust me that this is where it's going to end up. So now I'll actually show you the results. Okay, so of course, luckily we already have the results of a numerical experiment. We have our spectra for hydrogen that we calculated, and this is these black dots here, which is the same points that I showed before. And now the green curve shows the reconstruction based on this procedure. And so the first thing to notice is at low intensities, at least, we get ionization times of exactly 0. So this tells us that the electron came out exactly at the peak of the field. So no delays, nothing. The electron just appears exactly at the peak of the field. At higher intensities, something a bit funny starts to happen, and we actually see that the electron comes out before the peak of the field. And I'm going to come back to this in a second, but for now, let's just notice that the times are never positive. So this tells us that there's really no room for tunneling delays. The electron never comes out after the peak of the field. So for hydrogen, at least, we can say that there are no real tunneling delays associated with the electron's motion under the barrier. Okay, so now let's have a look at this thing that happens here at high intensities. And of course, there's something else that happens at higher intensities, and that's we get more and more ionization. So we can look at the depletion of the ground state population as we go to higher intensities, and indeed, as we'd expect, it increases with intensity. And then based on this, we can try to estimate, so if we're losing population from the ground state, of course, before we reach the peak of the pulse, then, well, it's going to be better to ionize earlier because there's not so many electrons left later on. And we can estimate the degree of this effect. This doesn't really work anymore. We can estimate the degree of this effect, which is shown in this red curve. So this is how much we'd expect time to be modified by the effect of depletion. And we can see that it explains a good part of what we see in the green curve, but maybe not completely. And the remaining discrepancy between these two could actually reflect some sort of other non-trivial dynamics. We have some evidence that there's some Rydberg states are populated and so on, so maybe there's some sort of ongoing ionization dynamics that happen even after the electron comes out from the barrier that could lead to some preferential for it to be better to ionize earlier. And then, just before I finish, I'd just like to talk briefly about multi-electron effects and what we can see there. So we have some early calculations that have been done for a simple 2-electron system. So this plot shows the difference in the offset angles that we measure for a 2-electron system compared to a 1-electron system with the same ionization potential. So first, the black dots are for a 2-electron system with a high ionic excitation energy. And in this case, we see that the offset angles are slightly reduced compared to the one electron case. And this is actually quite easily explained by polarization. So in this two electron system, the electron that's left is also pulled by the laser field. And as a result, this shields some of the positive charge from the outgoing electron, so it doesn't experience as much of a Coulomb deflection. So that's why the angles decrease slightly. Now, the red curve for a system with a low ionic excitation energy is even more interesting, because in this case, we see that the angle starts to increase as we go to higher intensities. And this increase is actually associated also with the onset of double ionization. And as we go to higher intensities, the spacing between the emission of the two electrons becomes smaller. And this tells us that there's the ion must be getting excited. It must be getting excited by, together with the electron that comes out. So we could be having some double ionization, double excitation of the ion, or creating an auto-ionizing state or something along these lines. And this could be some sort of real delay induced by this electron-electron interaction. So this could be something quite interesting to look into. And it seems the outer clock could be sensitive to this sort of thing. But here, I'd just like to sum up. So we've looked at the outer clock experiment and talked about how this can help us to time resolve the process of strong field ionization by making use of a mapping between angle and time. Also talked about the analytical R-matrix method, which is what allows us to come up with a mapping, what this mapping actually is, which is then what will allow us to extract the time from the angles that we measure experimentally. We looked at the hydrogen atom, and for hydrogen we've seen that there's no tunneling delays as such, and that the offset angle that we see can be explained completely by the electron-core interaction. And finally, we know that this work now calibrates the outer clock, and hopefully this will now open the way to study multi-electron dynamics in the future. And I'd just like to acknowledge the many people involved in this work. A lot of them are in the audience. So yeah, we've got Olga at Misha at MBI, we've got the 3 different groups who were doing our calculations for hydrogen and Ukava, and Seren, who did the 2 electron calculations. And thank you very much for your attention.